All right. Welcome back. Passing around attendance per usual. Need it a second. Yeah. Already October. Look, you know, why are these buttons upside down? All right. So today we're going to continue SN2 reactions, and then in lab, in addition to IR, we're going to introduce mass spectrometry, okay, which is not in the manual. We'll have a little discussion on mass spectrometry because I'm not going to have time to talk about it during lecture, most likely, okay? All right. So I think last time, all right guys, let's come together here. Last time we wrote out like a reaction, but we didn't actually draw any structures, right? Sodium iodide plus S2-chlorobutane, and we use acetone there to as our solvent. All right, but now let's go over how that reaction takes place. All right. Whoops, don't want my eraser. All right, CH3. All right, so our iodide here, remember, SN2 is backside attack. All right, so partial bond here is forming to the carbon atom. Partial bond to the chlorine is leaving. And then here, it looks like around the carbon, there's a trigonal planar arrangement because the partial bonds are not actually bonds yet. Okay, so it looks like we have a trigonal planar arrangement of atoms here. CH2, CH3. Okay. Double dagger here. And what we get here is we get our carbon atom will now have the opposite configuration of stereochemistry. Okay, so now the CH3 is pointing this way. And then the ethyl group here, CH2, CH3. All right, Cl minus will stick around here as the ion. So notice here, charges are conserved, right? And then if we were to assign R and S, the stereosonics here have switched, okay? But we're not going to assign it right now, just because it'll require a bit of work as drawn, okay? So let's not worry about that yet. All right, so here we have backside displacement. Okay, and we know here these are both chiral. So now the product is chiral and optically active. What about the reactant? What can we say about the reactant? Chiral? Yep. What about optically active? Yes, because it's chiral and there's no mirror plane. There you go. Okay. All right, are any questions on that? Any questions about the kind of like the mechanism here? Backside attack, and the chlorine is the leaving group. Okay. So we know it's a one-step process, right? So let's talk about the orbital picture. Like, what's actually happening here? Why does it go this way and not the front side attack? There's an steric argument, and then there's an orbital argument, okay? All right, so stick with me here. All right, so let's do the orbital picture. Of the SN2 reaction. Okay, so let's look at our nucleophile. It's negatively charged. Okay, so for your nucleophile, the negative charge sits in an hybrid orbital. So remember, the nucleophile here, we would consider it, if we had an oxygen atom, or like a nitrogen atom, those orbitals will sit in a hybrid orbital. All right, so let's draw something like this, little lobe here, and then a big lobe over here. So this is where my electrons will be, okay? And I'm going to shade this kind of black here. All right, but my dots here, my electrons are still there, okay? So right now at this position, we have tetrahedral centers, so tetrahedral, okay? And now let's draw our carbon atom. So to make this easier, I'm going to denote the groups as different R groups. So R groups could be any alkyl chain or any group that's not the same as the other R's, okay? So I'll do that one double dash R, R dash here, and then well, it doesn't matter here. R with no prime. We call that prime, not dash. Sorry. Okay. So if we look at the orbital picture here, bonding takes place when you have a filled orbital with electrons and a non-filled orbital with no electrons. All right. So this is where we go back to molecular orbital theory. All right. So this right now, the nucleophile is not bonded with anything. So it has no, these electrons here have no molecular orbital. It's going to form one as we do this reaction, okay? But this one right here, this one right here, this is called the, this will be called the, let's see what I call it. This is the Cl sigma star orbital, anti-bonding. All right, so this orbital right now is unfilled. All right, the reason why it's unfilled is because if it was filled, if there were all 2 electrons in there, it will not promote bonding. That's why it's called anti-bonding. Anti-bonding orbital is unfavorable. Remember what we talked about way at the start? Okay, so this orbital is unfilled. This right here is a filled orbital. All right, so the filled orbital on the nucleophile will want to interact with an unfilled orbital on the electrophile or the carbon atom, okay? So what happens here is that this bond right here, so this anti-bonding orbital right here, is going to be filled with the leaving group, all right? So the leaving group right here is already filled, okay? All right. That's right. All right, I think that should be good enough. Okay, so what happens here is when these two approach, what's going to happen is you're going to go to this situation right here. All right, so let me see if I write this small enough. All right, it's all right. We might have to go to a different page here. All right, so as the nucleophile approaches, you're going to start forming a bond, okay? So what the nucleophile does is its orbital is slightly going to change here, okay? And then what happens here is that this orbital now it's getting smaller, and it looks like it's going to bond with this carbon atom here. Okay, like this one. So now you see here, these are now at the same color. So now it's forming a new bond. The bonds are overlapping. Okay. And then the carbon atom here is starting to become that shape we saw earlier. Okay. And now the leaving group orbital is still here, but the orbital now is looking like a p orbital, and it's being taken away by the leaving group. So this is our transition state still. Okay, so the nucleophile approaches. Its electrons are being shared now in the transition state with the carbon atom, forming a new bond. Okay, so the reason why it looks like this is because what's happening here, only certain color lobes can interact. Okay, so it has to deal with the sign, orbital overlap, right? Because what happens when we have waves of the same sign? When they interfere with each other, what's that called? What kind of interference? Now let's go back to like physics. So waves. So when you have waves of the same sign, right, they tend to add and become bigger. What kind of interference is that? Constructive or destructive? Constructive. So to form an orbital or get the maximum overlap, you have to have orbital lobes of the same shade or color or the same sign. All right? So the nucleophile can't interact at the front there, okay? Because what happens when it interacts in the front, right here, that shade of color, right, is opposite of the nucleophile. So that's called destructive interference. There will be no bonding to occur at all. Okay? So to explain bonding and these type of reactions, you can go so far with just like what I've been telling you. But if you don't talk about orbitals, some things that are facts, they're hard to to explain and wrap your head around. Okay? So this is the orbital argument. But now let's, so guys, if you have room, I don't have room, but I'm going to go to a new page, okay? And I'm going to draw the arrow here. So now my product, what happens here is our nucleophile and our carbon atom here, okay, are now bonded together. So don't worry, you don't have to reproduce this picture, but this is just to help you understand like where this is coming from, okay? So now see here, this is tetrahedral. So we've gone back to the tetrahedral center, all right? And the transition state, that was a trigonal planar arrangement. So if I can I go back? Let's just, right here, this is trigonal planar. Around this carbon atom right here. So that geometry is planar. It's going to a planar transition state. And then we get to the tetrahedral arrangement right there. All right. So let me just shade a few colors here. Nucleophile.
On the trigonal planar, is that you're just counting the arbitals?
Yeah. So don't count the partial bonds. Those are bonds, so you don't consider them. Yeah. All right. And then also here we have the leaving group. And the leaving group now, since it doesn't have a bond, it has now gained its p orbital back, okay? So now it's a lone pair right here. And sorry, don't put the lone pair there. Erase that. Put the lone pair in here. Let me just write in red so you guys can see it. Red dots right there, okay? All right, so this leaving group now. So let's kind of just annotate what happened. So now we have a p orbital. So this is the p orbital here on L. P orbital on L. Now, if this is tetrahedral, this nucleophile now has an sp3 orbital. All right, sp3 hybrid orbital. Now let's look at this now, and let's assign the orbitals to the transition state. Okay, so let's go back a page here. Okay, so what's actually happening here is you're going from a p orbital to sp3, and then this bond broke, so this is actually going to, so this one here, so you have a sp3 orbital going to a p orbital here, all right, and that's for L, all right, so this is for L. Let's just put in parentheses for L, okay? So L was bonded through sp3 hybridized orbital, but now, since it's becoming with no bond, it just gets back its p orbital that it used to hybridize, okay? So this L now is no longer considered tetrahedral geometry, and because it's not bonded to anything, the leaving group, it's just an anion, in our case, maybe chlorine or iodide, so it's no longer in a bond. Okay, but carbon here, carbon will still remain sp3 hybridized because it's just swapping partners. Okay, so here, this nucleophile here is in an sp. Well, we could just say here. Let's just say it's a hybrid. Well, it should be a hybrid orbital. So say these lone pairs are in an sp3 hybrid orbital. Okay. What I meant to say here is that this carbon in the front, you see the carbon here? So this carbon, so let's just highlight that. So this carbon right here, okay, its bond broke, so it's a p orbital again, right? But now, since it's forming a new bond, it's going to sp3 because it's bonding with the nucleophile. Okay, so that's how the bonding orbitals kind of change here. It's a little confusing to keep track of, but just think of these orbital pictures. That's actually what's kind of happening between the orbitals in this diagram. Okay, and so if we label these here, carbon originally here, sp3. Okay, and this leaving group, we can actually consider it sp3 or just p. In this case, let's just consider it. If it was oxygen, right, it'll probably be sp3 hybridized, or nitrogen, it'll probably be sp3 hybridized. So this, we'll just consider this leaving group here, sp3 hybridized, because it's bonded to the carbon file. Okay? So those are the changes here. What we need to realize is that the orbitals are changing shape, and we go from breaking the hybrid orbital, because that bond broke, so we can't explain it using hybrid orbitals anymore. And then it reforms the hybrid orbital because it's forming one with the nucleophile. All right, but this is a picture of like what's actually happening. Like, we could draw arrows all day, but the bigger picture is what's happening with the orbitals, and that's chemistry. Okay? All right, I know that was a lot, but are there any questions? Okay, so that's just the orbital picture. What I want the takeaway here is just how the electrons are transferred through the overlap of atomic orbitals. Okay? All right. Yes. No. This is just the MO diagram, yeah. In grad school I did, but not here. You won't have to here. No worries. All right, so now we got a good feel for the reaction. Let me see if I missed anything though. All right, no, okay. So now let's look at like what this energy diagram looks like, because to understand this reaction, it is also helpful to see how it changes with energy. Okay, but are there any questions before I move on? Nope. All right. All right, so let's draw the energy. All right, again, this is energy. So as you go up the y-axis, the energy is increasing, okay? Now we have reaction coordinate. So this is like the progress of the reaction. So as the reaction moves to the right, you're going to see this the changes in the nucleophile and the other and the reactant, the electrophile coming together. Okay, so here's our first energy state, and then we go to a higher energy state, and then it plateaus at the bottom here, like so. Okay. Well, let me just adjust that a little bit. They're not actually the same level, so it's lower in energy. Okay? All right, so SN2 reactions, they're usually, the product is usually lower in energy, but that's not a thing you have to really worry about. What's more important is how it proceeds, okay? So here you have your nucleophile, negative charge, plus R prime, C, X. Let's just make this a dash, sorry. R dash, and then wedge R right here. Okay? All right, and the transition state, what picture do we draw there? Like which picture that we drew in the previous page? Which one did we draw on the top there? Okay, we want to put it right here. Okay, so we're going to draw the diagram, or the picture, sorry, of the structure where the carbon now has two partial bonds attached to it on the horizontal axis, right? So the nucleophile is approaching, but also the electrophile is leaving, okay? So, all right, X here, gaining a partially negative charge, and the nucleophile here is losing its partially negative charge, so its negative charge is becoming a partial charge here. And then the R groups here, those bonds are not breaking, so they will stay like that. All right, like that. All right, and then on the far end right here, what do we draw there of the diagram? Yeah, the X group leaving, right? So now we have X minus plus X minus. And then our nucleophile is going to be attached to the carbon group now. R prime, like that. Okay, are there any questions about the diagram? So what you should realize is that the transition state, it has partial bonds, and that's because of the bond breaking from the nucleophile, forming a bond to the nucleophile, and the leaving group X is leaving and becoming the ion now. All right. So, how these bonds form and break? So the reason why it's simultaneous is because the SN2 reaction occurs in one step. And I think it might be helpful if we watch a little video on how this actually works, because it might not make sense on paper. Okay, so let's go back here and let me look at this part. All right, so let's look at reactions. So SN2, all right. Let's see, SN2. So see here, we can also look at your molecular orbitals. All right, so this was the orbital picture I was talking about. So All right, I got the colors wrong, but that's not important, okay? But what's important here, look at the nucleophile. What is it? Is it approaching the lobe of the opposite color or of the similar color? Similar color, right? So remember, the orbitals, we describe them as waves, right? They're waves that, all right, we describe the electron as waves, Schrodinger's equation. So what's actually happening here, these are actually waveforms, they're actually waves, but they're just pictorially represented, okay? So remember waves, if waves overlap and they're of the same sign, right? They're like the same sign here. You have two waves like this. All right. When we add these two together, how should the wave look? Bigger version, so something like this. All right? All right, well, yeah. It gets the points across. All right, now what happens if you have waves of opposite sign? Like this. What happens here now? So this is going in one direction, right? This is going in the other direction. Well, it's not drawing a scale, but they're opposite signs, right? So this will actually cancel out and it'll be flatlined, okay? So that's how waves kind of cancel out. And that's what's happening with orbitals. So you can't have this, see this red line right here? Let's use this ruler. Oh my goodness. So you see here, this orbital has to line up with that one. So you see if the bromine tried to attack the carbon through this area here, one, you're going to get some constructive interference, but there's also the opposite color lobe there, so you're going to experience some destructive interference, and that's why it doesn't go like that. It has to be good overlap, constructive interference right here, okay? All right. So let's just see here, and then this is the picture. What happens, you're going to form a new orbital. So the orbital now is drew the bond to bromine and carbon, and Cl has left as the leaving group. So now it only has its p orbital because it's unhybridized and not part of the bond anymore. All right, so that's why it's by itself. All right, and it's not shared. All right, so let's look at this movie right here. All right, so don't worry about those pictures. Those are molecular orbitals. All right, so remember, electron can be in the top lobe or the bottom lobe. Okay, so HOMO stands for highest occupied molecular orbital. Okay, and you see the bonding. That's how the bonding, the molecular orbitals are changing, and that's how the shapes come about. Okay. And LUMO there, that stands for lowest unoccupied molecular orbital. All right, you need those two to bond. All right, so it depends on which orbital you use from each reactant. Okay, but I don't want to go too much into detail, but I'll explain it using this graph. All right, so you get the best interaction if the HOMO here and the LUMO are closest in energy. All right, so this is from our nucleophile. All right, when two molecular orbitals interact, you get antibonding orbitals. You get a pair of antibonding orbitals and a pair of bonding orbitals. Okay? And here, this will be your, for example, nucleophile C bond. So this is your bond. So this is your sigma molecular orbital right there. Okay? So this will be our C/X antibonding orbital. And here, the nucleophile is pretty much in a non-bonding orbital, so it just becomes a non-bonding orbital. So we could just say this is non-bonding. Because the lone pair, right here, in the nucleophile, is this lone pair bonded to anything? Like for example, I minus. Is I minus bonded to anything? Right here, is it bonded to anything? What do you guys think? Is this bonded to anything? No, right? So that's why it's called a non-bonding orbital. It's not, and it's usually sp3 or a p orbital, but it's not bonded to anything. Okay. So for this one, the HOMO orbital, you want it to be as low as possible. Okay. You want this to be low as possible, but you don't want it to be too low or too high. Because if the LUMO is not close in energy, the amount of stabilization you get won't be great. For example, look at this example. What if our nucleophile was so low and our LUMO was so high? Okay? Right here. So the energy here won't be that great because it's so high in energy. So it's very close to the anti-bonding orbital. All right, so this would be sigma star. Okay? And look at here. So this is not a great match here because look, the stabilization is not that great. All right? So these two lines here, they kind of have to be parallel to your LUMO here. So here's the LUMO. And here's the HOMO here. And when you do the molecular orbital there, look at here. Is this energy that much different from this one? If you think in terms of energy here. If this was energy. Aren't these two very similar in energy right now? Yeah, right? So they're very similar. You're not going to get any, so not much overlap. Which overlap would equal more stable bond or stronger bond, so not more stable. So not much overlap, so you're not going to be not much more stable, all right? So not much more stable, all right? That's why we picked the LUMO to be on right here, and the HOMO has to line up right here, okay? So you get two situations here. When they're evenly matched, when these energies are evenly matched, you get the best overlap, and that's this case right here, okay? In the molecular orbital standpoint. This situation is if we flipped it. What if we use the lone pair on the LUMO here? So if we flip these, it wouldn't be good either. It look like this, okay? Something's very high in energy because it's an anti-bonding orbital, okay? Or we use one of these here, so it wouldn't be as great, all right? But that's just the orbital argument right here, okay? So what's actually happening, you have an unfilled orbital on the carbon, in the carbon molecule, all right? One of those orbitals is not filled, okay? But bonding interactions, right? You need to take this orbital and the nucleophile orbital and combine them, all right? So that's molecular orbital theory, and that's what's happening right here, all right? So they use the molecular orbitals to do that, all right? And I could just draw them right here. So the nucleophile one looks like this. The LUMO one looks like this. All right. That's essentially what they're drawing up there. All right. So this one, the loads will interact. They form a bond. But there's a reason why I'm not writing this on the page. This is just to explain the orbital argument. Okay. You don't have to draw this. All right. What I want to get around here is that bonding, you can't just draw arrows anywhere, okay? So you may see when we draw arrows, it's like, oh, can we just draw them anywhere? No, okay? So it depends on this kind of pairing. Where you start the arrow, it has to be from an atom that's willing to donate. That means the atom pair is stable, lower in energy, and it wants to give it to something that's relatively unstable, so something that's highly polarized, the CX bond, that wants to leave. It's high in energy, so if these interact, you can form a new bond and you break this bond here because you interact with it. All right? So, but there will be no homework on this type of stuff, so I don't expect you guys to reproduce that. But that's kind of the background of bonding. Okay? All right. So now let's look at a situation where it's not like this, but let's look at the nucleophile part of it. Okay. All right. So this is 2,1,4 hydroxide. All right. All right. Don't worry about this stuff yet. We'll talk about that later. All right. So this is the arrow, right? That's what we see. But let's see what actually happens. Like, is it really one step? What we mean by one step is that these two processes, bond making and bond forming, or bond breaking, they happen at once. Okay? So let's look at that movie here. Well, hopefully it's not narrated, is it? It might be. All right, let's look at it. All right, so there's the OH, right? It's the version from the back side. All right, and then you see here, it forms that intermediate, and then that's the transition state, right? And then as you go further to the products, it just ends like that. All right, so those bond, that transition state, in a transition state, you have elongated bonds towards the nucleophile and the leaving group. And then eventually enough push will be given, enough energy to get over the transition state, and you get to the product you want, okay? So I'll keep showing these type of videos just for now as we're learning mechanisms, but hopefully that gives you an idea of like what's actually happening. Yes, Monique?
Are these on Canvas?
Yeah, some of them are. The YouTube page for this doesn't have all of them. So, you can actually, there's an app for it, but it's like $5. On your iPhone or iPad, you could buy the app, which have all of them. It's pretty good. But the free version does have some of the videos too. So if you look at, so this is called Tap Chem. If you look for it in the App Store, it's still available. This is where you can find some of these animations too. And yeah, if I find some good ones, I'll send it your way just so you could watch them on your own time. But yeah, if you scour the internet, you can find some more of these videos. So I even could make some if I wanted to. I do have a program that I could use to make it. So maybe I'll show that sometimes. But that's how you would visualize those mechanisms there. Okay. All right. So that was a lot. Any questions so far? Are we okay drawing the mechanism of the SN2 reaction? Okay. So let's go back here now. All right. So now we talk about the mechanism a lot. We're going to have an idea like what the nucleophile does. Okay. We're going to talk about how to predict an SN2 reaction. All right. But first, let's talk about how we would use this to make something, all right? So let me I probably need a new page. So let's go to new page. All right, so let's do this example. Synthesis of an enantiomer. Oh, buddy. With retention of configuration by SN2 reaction. All right, so let's say we have this structure here. So this is a methyl group, alpha group, and we have a bromide. All right. So say we want to make something like this. H3C, CH2, H5, H, and CN. All right. So, all right, let's just start this early. Synthesis, a common exam type question. For us, it'll probably be towards the third exam and the fourth midterm, and the final. And then in second semester, this will probably almost always occur on every exam. Some kind of synthesis problem, 1 or 2 problems. All right. So my question for you is, how do I make this? If I were to make it, if I need to make it in the lab, how would I make it? Okay. So if you think right now, oh, we could just have sodium cyanide and just do an SN2 reaction. But what will happen if I just do that? What will happen to the configuration? You guys have to guess. So can I just achieve this by one SN2 reaction? No, because what happens to the stereocenter each time I do an SN2 reaction? It becomes the opposite, right? So if it's R, it goes to S. So that won't work. So right now, if we assign, so I'll just give this the sign to you, or the configuration. This is S2 bromo butane. All right. So the way you do this is that you somehow have to do 2 SN2 reactions, okay? So we noticed before that if there's a bromine on there or there's an iodine on there, they tend to do the SN2 reaction. So we'll need to make a product first that has either a good leaving group. We haven't talked about what makes a good leaving group yet, but for now, just think, okay, Br, I minus, those are 2 good nucleophiles and good leaving groups. Okay, and we've seen that because 1, they displaced the leaving group, and 2, they also left as leaving groups. All right, so first thing I would do is convert this to a different leaving group. So you can't do like you can't just put sodium bromide. It won't displace bromide because that's the same thing. You'll just get the same product. So there's no net gain to do that. All right. So there's no net gain in like energy. There's no driving force. All right. But one thing I could do is I put sodium iodide. All right. Okay. So the thing about this reaction is that if you do this in acetone, so let's use acetone, which is this guy right here. All right, acetone is actually, you can actually dissolve sodium iodide in there. But the driving force of this reaction, this reaction can actually go back and forth, all right? Because, iodide and bromine, they're both good nucleophiles, and they're both good leaving groups. All right, let's just recognize that. So the reason why this reaction goes is because the product here, sodium bromide, is not very soluble in acetone. So it will drive an equilibrium to produce just the iodide reagent here. Okay? So if we do this reaction, the bromide here, reaction with sodium iodide, what do you think the product is? Yeah, good. R, iodo, right. So this will displace the bromine. R2 iodo butane. All right, and you'll get sodium bromide. As a solid, this will crash out. Will crash out of solution. All right. So that's your driving force. If something crashes out of solution, it will push a reaction forward all the way. Sodium bromide. This is something you don't have to really pay much attention to, but that's just a kind of like experimental kind of thing. Okay. So SN2 reactions, they can actually go back and forth, but you can devise a reaction so you take advantage of something like equilibrium and drive it forward, okay? But that's something we'll come back to later, so don't worry too much about that. All right, so now how do I get from here to here? That's my first product. How would I go from my now R2-iodobutane? How do I get a cyanide or CN group on there? All right, so remember CN, cyanide, remember cyanide ion from Chem? That's negatively charged. So you need to use a salt. So common salts here are sodium, potassium, sometimes lithium, sometimes not. So how would I get cyanide in there? All right, let's do this one. All right, potassium. Let's just use sodium. Potassium's too dangerous. That's all right. Sodium's not that much safer either. All right. So the reason why we use acetone, one, our reactant is organic and it's polar, so we need to use acetone. And acetone is the only one that can dissolve salts. Or like you need a polar solvent to dissolve something that has charges or ions. Like sodium cyanide, that's a charged species in the solution, right? To get into solution, you need something that's polar, a polar solvent, like acetone. And acetone's polar, right? Because we know there's a dipole moment right here, making acetone polar. Okay? The reason we don't use water is because most of these things won't be soluble in water, the organic part. So water is not an issue, is an issue there. And sometimes water can interfere with your nucleophile, which we'll talk about, okay? All right, so if we do this, right, do this step, we now get what isomer there? We get back to S, right? So that's how you would perform a stereo-specific reaction, where you need just one enantiomer. This is the way to do it. Although it's kind of time-consuming, but that's okay. So this is S2. All right, so this name is not going to sound familiar because we haven't talked about this yet. So this is 2-methyl butane nitrile. So this is how we number it. So in this case, CN is now the priority. So we give this the 1 position. 1, 2, and then this is 3, 4. All right, so that's why it's 2-methyl butane nitrile. So that's how you name CN groups. They're called nitriles. Okay, so guys, if this is confused right now, don't worry. We'll do a lot more practice with this, okay? So remember, if you want to invert a stereocenter, you have to do an SN2 reaction. Yeah, Maria? Oh, because there's 2 carbon atoms right there. C2, H5, yeah. Sorry about that. I should probably write it out. All right, so we're going to start talking about, we'll start talking about the leaving group. But first, I want to show you a situation where what if you have two carbon atoms with good leaving groups? Okay, so let's go over that first. All right. Boop. All right, so let's title this SN2. reactions of molecules with two stereocenters. All right, so let's draw a Fisher projection. Let me erase that. All right. All right, so sometimes on exams, you may see this phrase, excess. What does excess mean?
More than you need to.
Yeah, more than a stoichiometric amount. So more than a 1-to-1 ratio, right? So for example, look at right here. In my starting reactant, I have two chiral centers, and they both have halogens, so good halogens, as leaving groups. So bromine can potentially be substituted, but also chlorine. Okay, so Ki, if we add iodide in excess, so in theory what we're adding is I minus, so I minus here, the source of I minus right here, okay? So when you do that, what do you think is going to happen? R All right, so that's the name of this compound. Now, what do you think is going to happen if I had excess of I minus there?
Is it gonna replace both the chlorine and bromine?
Good, yes. But where would I position the iodines now? All right, so it's SN2 reaction, right? It's going to flip the what? Yes, it's going to flip to the opposite enantiomer, right? So CH3, CH3. So in this case, the H will flip because we're changing that stereocenter, right? So the easiest thing to do is flip the two horizontal groups. So I would change here. All right, where would I go on this on the third carbon? So the second intersection there. On the left. There you go. So here we have 2s, 3s, 2, 3, diiodo butane. All right, so let's do another example. See if we can connect this to a different example, okay? So say you have this compound. Yikes, what was that? So we have sodium diolate, smelly, not good to work with excess, okay? So, all right, well, I'm gonna take a few minutes here. Think about what the product should be. If you got an answer, share it with when you get an answer, share it with the person next to you. And we'll come back and draw the rest, okay? All right, so, discussed here, think of the example we just did. Think about what you know about SN2 reactions and how they work and draw the product. All right. So remember, sodium here does not do anything, so don't add it to your product. What's the actual important part of this is the SH. Think about what charge that has, okay? Just think of the example of Ki, how we got I minus from that, okay? All right. flipped it. Which one's the 2? Bromine comes in from 3. So that should have like 3. So you can do 1, 2, 3, 4, right? Or 1, 2, 3, 4. So this makes it. Yeah. So this one should have 2 positions. So bromine being comes in in and out. All right. So let's go over this before we take a little break here. So what did we get? So what does the product look like? Okay, good. So we substitute, but then we switch to the opposite enantiomer on both stereocenters, right? So we get CH3. Now tell me, is this optically active? You so? Catherine, what'd you say? Yeah. Good work. Does everyone hear that? So this will not be chiral. So by doing this reaction, you have destroyed all optical activity. Okay, but sometimes maybe that's just what you want. Okay. So this is actually a meso compound, so it's achiral. We know the mirror plane will split this molecule in half right here. So it's achiral, all right? But you can still sign R and S, okay? And so you can still sign R and S, but sometimes, you might just have a situation where it's achiral. All right, so dio. Don't worry, you don't need to memorize how to name this. It's didio. All right. All right. Are there any questions on that example? No? All right. So let's take 10, and we'll come back and talk about leaving groups. Okay? That's our next section here. Yeah, don't worry. So that's why this gets the 2 position instead of this. Oh yeah, so it doesn't matter. In this case, we were referring to how we originally wrote it. Yeah, so this is 1, 2, 3, 4. So what's happening? Remember, in the horizontal, right? Isn't that the wedge form? So the H is on the back. So if the H is on the back, it's the opposite of what you see, yes. Or else you have to rotate it, but that is not how it works. Yeah. Okay, but that's how we would get around that.
Originally it was R, but
Yeah, so that's why it's what is this shirt doing here?
I just the area I want in here. Oh, thank you.
Yeah, they still could have chiral centers, but it does put in symmetry. It makes it achiral. Yeah.
They're,
Oh,
they're
yeah,
good.
because
So
it-
it's
it's
pretty
fine.
fine. The car was in our street. The car was in our street. But she would say like, start off as like Boulevard. Yeah, start with like finding.
Oh, no, I thought it was, it was someone that she had.
Yeah, the practice was great.
It was like this. More than to me, so. It was like practice ones. Yeah, like that. It's like a, and they're both going out.
Our is right, and that's his left.
But if you look at this one, what
It's like you just have to,
that's what I'm but what if this one was a
yeah, you have to have and the sheet is here, is like she just rearranged it.
So this one would be,
Instead of it being like flip this way, it she just rearranged the configuration of it, so it's like, the image is still like, because it's so similar already. Yeah, with this carbon, it's hydroxide. Same thing over here, which is a different configuration, because this carbon is not going to be out, so this one has the hydroxide. So it's still, because they're so similar, it's still a mirror image, but it's just, she just wrote it here. She flipped it. Yeah. Yeah. Basically, through this like copy of it, we flipped it because that is still a mirror image here, which is only this way. And it's just like that. So mirror image is always just yeah, but the mirror, it doesn't always have to be down this, it could also be this way. Yeah. But they're like blue light. So it's not expensive.
What's up? Yeah, so either you can turn that to me and I'll grade it by hand, or you can turn it to the assignment. It's either, yeah, if you want. They're due, they're due, you can turn them by the second term, so you're not done with the debt, because you still have to.
Oh, okay.
Yeah, just turn it in the latest. Yeah, you can hand it to me, yeah, online, if it's online, just make sure you write the question.
Okay, yeah.
And just know, how many points you missed, so I know that. Well, if you correct it, I'll probably, if you correct it correctly,
Yeah,
I'll get up, I'll give you close, I'll give you touchdown.
Okay.
Yeah. Yeah, can you run over here? Yeah. Yeah. Yeah, so there's two ways, draw the actual mirror image, or draw the same, draw this structure, but make it both dash. Yeah, there's two ways. Hey, what's up?
26, I was looking at the solution, was saying solution substitute one is the higher grade. No, I don't know. There's the like, the end of it is like the explanation of the solution is wrong.
Oh, you need the second part.
So it's saying substitute one is the highest grade. Even though difference is not. Yeah, I got that one.
The order is great.
Yeah.
about how many carbon atoms are
Shape it to the bottom part, and then have this part left.
Alright, that one. And that one's the other one, right?
It was like, it's sort of, but like, because I remember
Yeah, you get the most, the orbital form, right? Most overlap, that's why it's so low in energy. Whereas they're so different, this one's gonna be so close energy.
Right.
But it's very hard to know how exactly how high it goes up. You have to do calculations. Like MO calculations. So, yeah, but the reason why it goes that way is yeah, so it would make more sense in terms of like scarats. I usually agree with that. Purists won't like that. So. Alright. Oh yeah, both are again. No, please, no. Yes. Okay. Sorry, yeah, the temperature always fluctuates. Hold on. Yeah, question? No, I'm Makes sense? That's why there's so many resources. Yeah.
Thank you so much.
No, there's only three groups around. Three groups, right? Yeah. That's what we're doing. Yeah, so basically a tetrahedral center, that's planar center. All right, guys, let's come back in. Hopefully, it didn't wander off too far. All right, so we haven't really talked about like why do these reactions happen in the first place? Isn't there a situation where this won't happen? Yes. So this is like one of the most studied reactions. It's very common. I even use this reaction in synthesis, so it goes full circle here. Okay, so we're going to talk about reactivity, and a big part of this chapter won't be a focus on this exam in much detail, but further down the line, we'll have to say, oh, is this a good SN2 reaction? Is this an SN1 reaction? Like, what type of reaction is it? So we'll have to be able to do that. All right, so let's talk about reactivity and leaving group ability. All right, so for the leaving group, there's a few criteria we have to do. All right. So leaving group. Here, all right. So the leaving group must depart as a weak base. Neutral or ion, all right? So there's a trend here. Remember, the weakest base is the most stabilized. So the most stable base are the easiest to leave because they don't care. To react again. Remember? So conjugate bases of the strong acids, those are the best leaving groups. Our point here, Cl, HCl, good leaving group. We saw that. Br, good leaving group from HBr, and iodide, good leaving group because of HI. So they're the conjugate bases of strong acids. So in this case, we could say here, or conjugate bases of a strong acid. All right. So that, even though this thing has a charge, it has to be a weak base. Because if it's a strong base, it'll just want to react again. So it has to be a weak base. So a conjugate base of a weak acid are the best. Okay? All right. All right. So for here, we can say, let's see what I want to say here. All right. All right. All right. Because the leaving group, right? What happens to the leaving group? What charge does it carry as it leaves? The examples I showed you. Negative. All right. So if it has a negative charge, it can't be a small atom. It can't be oxygen. It can't be nitrogen. And it can't be fluorine. Those are the worst leaving groups. The best leaving groups are the ones that are large or resonance stabilized. So think of our acid chapter where we said, okay, the weakest conjugate base is the most stable. That acid is the strongest. The same thing for leaving group ability. It has to do with the pKa of its acid form. Okay. All right. So let's go into more details here. So let's do. We mentioned base, right? So let's go over what is basicity. Okay. So let's refer to that right here. All right. How well a compound, so in this case, is acting as a base in chemistry, right? That's where you take a proton away, right? Shares its lone pair with a proton. So in this case, any H in the molecule, okay? So any H in the molecule. All right, so here, the stronger the base, all right, the better it shares its electrons. All right. So in order for it to share its electrons, it has to be able to form a bond. So if it can't form a bond because the electrons are too stable, they're just happy where they are, there's no benefit to forming a bond. So like the halogens, Cl, Bri minus, they don't like to go backwards because their electrons are pretty stable. They have an octet and they don't really want to bond again. That's why they're considered strong acids. Okay. All right. So, oops, my bad. Let me go over here. Two phrases I want you to remember about basicity here. The weaker the base, the better it is as a leaving group. All right, so that's something we should remember. So let's just, I don't know, do something. Circle it, box it. I don't care. Just make sure you remember this correlation here. All right, and the other thing we should recognize here is that stable bases are, all right, if a base is stable, is that a strong base or a weak base? Let's think about that. If it's a strong base, that means it wants to give away its electrons. So it wouldn't be considered stable. So stable bases are ones that don't want to act as a base. They're happy as they are. So we're called them weak bases. All right. I boxed this one too. All right. So we have to look at the periodic table and the trend in base strength. Okay. So well, you can't. You can write this trend if it's hard to remember on the day of the exam, but you can't write it on a periodic table and bring it to class. So try to remember this leaving ability. All right, so let's talk about the halides. So leaving ability of halides. All right. So I minus is the best. BR is good. CL is okay. And F is flat out lousy. All right, so lousy slash horrible. Weak. So not the best, but it will go. It's okay. All right. BR is fast, does the job. I is super good, so super fast here for iodide. The problem with iodide is it tends to do redox reactions, so that's an added complication. But for our purposes, it doesn't matter. You don't have to worry about that. Okay, but in reality and practicality, no one uses iodide because the bromide works just as well, and it is not sensitive to redox, so that's why we use that. All right, so I will make a note here. I will mention that fluoride is a good nucleophile, but I will not show you like much examples because they are very rare. They're very rare in the chemical literature and research. So I'll make this little note right here. SN2 reaction. So most of the time you won't even see fluoride in problems other than my lecture note, the lecture notes and stuff you may find online. Okay, so SN2 reactions are rarely observed with fluoroalkanes. So that's why it's lousy. They're rarely observed. They're too slow. That's the truth. They're just too slow. Okay. Are there any questions on base strength and leaving group ability? Just think, if your base is too strong, the bond itself must be too strong to break, or else it'll just form that bond again, right? It's a base. It'll just form that bond again. A weak base, easy to break, and there's not a likelihood that it will form again. So that's why they leave, and this reaction occurs the best with iodide. Okay? All right. Are there any questions? No? All right. Well, guys, after today, I'm working on the homework, and I asked some of these type of questions, like what's the best leaving group? What's the good nucleophile? What's the best way to do this reaction? So stuff we went over today, okay? All right. So now let's talk about these leaving groups and see how they differ in reactions, okay? So let's turn the page here. Let's do relative reactivities of alkyl halides in an SN2 reaction. All right. So RI has the best leaving group, so should I react the fastest or the slowest? The fastest, good. All right, so R here just stands for alkyl chain. So let me just say that. R equal alkyl group. Okay, so here, most reactive. RF here, 2 unreactive. So this is the least reactive. 2 unreactive to undergo a SN2 reaction. All right, so RF won't work. Well, maybe that's why, polyfluorinated hydrocarbons, they tend to stick around for so long. They're unreactive with anything, and you need like microbes to try and break it down. So they're strong bonds. The CF bond, pretty strong bond, so that's why they're not very reactive there. All right. So that's for the halogens. Now, what if we go across a row? What's the trend there? So we know the trend is from down a column, the leaving group increases. Fluorine is the worst, right, on the very top, and then iodide's the best. Now let's think about across a period, okay? So here, basicity of conjugate base, increases from right to left across the periodic table. Okay. So let's make a trend here. Here's the strongest base. Here is the weakest base. All right. So let's look at carbon, the fluorine. All right. Which one has the highest electronegativity there? Carbon, nitrogen, oxygen, or fluorine? Fluorine, right? So the higher the electronegativity, the more stable the base. But now, remember, we're comparing this across a row, not down a column. So F here is the weakest base. Why might that be? If you have a higher electronegativity, do you want to share it? No. So that's why it's the weakest base. All right? And it's the weakest base, right? Because HF is a stronger acid than H2O. And that has to do with electronegativity. Okay? So if we're comparing the ions here, the conjugate base, OH minus for water, the conjugate base of water. All right. What would the conjugate base of ammonia be? NH3. No, you're close. Go backwards. NH2. So we'll see this base. Wish we could use it, but I don't think we can. It's too dangerous. So this is an amide. So that's not ammonia no more. That's the negative conjugate base, of ammonia. That's called an amide, which we also call one of the functional groups. So it's kind of confusing there. All right. And the last one for carbon. Carbon is the best base. Why do you think carbon is the best base? If we have a carbon nucleophile, CH3 minus, what do you think is going to happen? Is it going to stay like that? No. It's going to react as soon as it finds a hydrogen of any type. Doesn't matter if it's H2 gas, it will deprotonate that. Okay? That's how reactive it is. So that's the strongest base. Okay, so next time on Tuesday, we'll talk about some other leaving groups. There's another class I want to touch upon that you'll see in this class for reactions. But if there's no more questions, I'm going to start passing out the quiz. Okay?